But there's one bigger problem that this white dwarf can have. It causes much more of an issue for it, okay? And that is this. Let's say that white dwarf had a mass of, I don't know, 1.2 the mass of the sun. Let's say that's what the white dwarf has. And let's say it starts to build up a disk. But the conditions don't get right for the disk to explode. So the disk doesn't explode. But the white dwarf keeps pulling more material. So the mass keeps going up. Why could this be a problem? Why would this be a problem for this white dwarf? Well, it's because there's a maximum mass, right? What was the maximum mass that a white dwarf can hold? What's the max mass? Just give me a number. That's okay. 1.4. There, yeah, you got it. 1.4. 1.4. 1.4 is the limit. 1.4 times the mass of the sun. That's the maximum that the electrons can hold. So if the disk fails to explode through a nova and it continues to build up, eventually the mass of the white dwarf plus the mass of the disk will hit that limit. And then that's a big uh-oh, because then the electrons can't fight gravity anymore. They were like fighting each other by pushing each other apart. It would be like all of the electrons' arms suddenly broke. Just blah. They were trying to hold each other apart, but their arms broke. And so what does gravity get to do at that point? Gravity has been waiting this whole time. As soon as gravity sees that the electrons can't fight anymore, what will gravity do to the white dwarf? Crush. It's just been wanting to crush this whole time. It's just wanting to just smash this thing the whole time. And so finally, once the mass hits this limit, the electrons can't fight back anymore, and so gravity goes, here we go, and just crushes the white dwarf. Just, psh. But what that does is material is coming together from all sides, and what will happen is that the material coming in from this side hits the material coming in from this side, and it bounces, it rebounds. So what's going to happen to the white dwarf then? If all of its material came slamming together in the very center together all at once, and then all rebounded, what's going to happen to that white dwarf? It's gonna explode, yes. It's gonna explode. So if the white dwarf hits that limit, it just blows up. And if that is a star exploding now, what does that mean it's gonna be called? Now we finally have a star exploding. So it's not just a nova. Now it's a supernova. So if the white dwarf's disk pushes it to the limit, it has, let's call it a white dwarf supernova. Which means it explodes. Just like high mass stars explode in the last few videos, okay? Can this supernova happen over and over again? Can the white dwarf just make a new disk and make a new supernova? Yes or no? No, it can't. And why can't it? Because the white dwarf is gone, right? The white dwarf is gone when it supernovas. So that means there's nothing left to make a new disk and make a new explosion. So novas, regular novas, can happen over and over again. But once it hits supernova, that's the end of the road. That's the only thing that gets rid of a white dwarf, essentially. The main thing. Now, two things I want to say about this supernova before we move on to the next major topic. Would it destroy the other star? That's a good question. Most of the time, I would say no, because even though that's an extreme explosion, stars are just so big and massive. It probably would blow some of the material off of that star, but not enough to probably even notice that there was a difference if you were looking at it from far away. Good question, though. Stars are just big old things. Now, two quick things. In the example I gave you, the white dwarf started at 1.2, and it blew up when it was 1.4. It doesn't matter how big the white dwarf is in terms of mass when it comes to this supernova. If it started with 0.8 mass of the sun, it still would not explode until it hit 1.4. Okay? It still would not explode until it hit 1.4. So that means that every single white dwarf supernova explodes at the exact same mass. It's always, no matter how much you started with, you only explode when you hit the limit. And that means that every single white dwarf supernova has the exact same brightness. Okay? It has the exact same brightness. Every one of them looks essentially identical. Okay? And that means it's really easy for us to figure out how far away a white dwarf supernova is, because we know that they all make the exact same amount of light. So by looking at how dim they look, we can tell how far away they are, using the same methods that I talked about in the last couple of videos. In fact, we say that a white dwarf supernova is a kind of standard candle. And a standard candle just means a thing that has a known brightness. Okay? And the last question I have about this, before we talk about another kind of dead star, that won't take as long as white dwarfs. My last question is this. Will our sun's white dwarf ever have a white dwarf supernova? Or a regular nova? Will our sun have to worry about these problems? Yes or no? No. No, it won't. Because what has to be right up next to the sun in order to have these problems? No other stars. That's right. There's no other stars. The only kinds of white dwarfs that will have these problems is ones that are already orbiting other stars, okay? There's no other star next to our sun, so it's not going to have these problems. So our white dwarf will be one of the ones, the more common kind, that just gradually does nothing. Yeah, does nothing and slowly cools down. That's right. Okay, so that's everything about white dwarfs. I want to real quickly talk about one other type of dead star. It's not going to take nearly as much time as white dwarfs because this other kind of dead star is very similar to a white dwarf. Just want to go ahead and get it out there.